think about this for a second. A cruise ship, right? Huge thing, tons of metal just floating there.
Mm-hmm.
But you drop a tiny little steel ball in the water, sinks instantly.
Yeah.
Or like a helium balloon just shooting upwards. Seems weird, doesn't it? But it's all physics.
It really is. And that's what we're diving into today. Density, relative density, buoyancy, the whole principle of flotation.
Yeah, we've got some good material here, some educational stuff that lays it all out.
Exactly.
And our mission really isn't just to list definitions. We want to get the why. You know, why things float, why they sink. Get those aha moments.
Definitely. Those moments where it just clicks.
Okay, so let's start at the bottom layer.
Yeah.
Density. What are we really talking about?
Okay, so density, at its core, it's about how much stuff is packed into a certain space.
Stuff meaning mass.
Exactly, mass. The technical definition is mass per unit volume. So imagine two identical boxes, right? The one filled with lead is denser than the one filled with feathers because there's more mass crammed in.
Gotcha. And we use different units for this depending on the system. SI versus CGS.
Precisely. SI, the standard international system, uses kilograms per cubic meter. So kg.
Okay.
And the older CGS system uses grams per cubic centimeter, GCM.
Right. And knowing how to switch between them is probably useful. Is there an easy way?
There is, actually. It's pretty straightforward. 1 gram per cubic centimeter equals exactly 1,000 kilograms per cubic meter.
1,000. Okay.
So GCM to kilogm, you multiply by 1,000.
And the other way, kilogm back to GCM, divide by 1,000.
You got it.
Okay, let's make this concrete. Water. The source says its density at 4 degrees C is 1 gram per cubic centimeter. What does that actually mean?
It means if you take a tiny cube of water, 1 centimeter on each side, about the size of a sugar cube at that specific temperature, its mass is exactly 1 gram.
Simple enough. 1 cubic centimeter, 1 gram. Okay. Now, something like mercury, way denser. The number here is 13.6 times 10 to the 3 kilograms per cubic meter. Sounds like a lot.
It is a lot. 13.6 times 10 cubed is 13,600. So imagine a box, 1 meter by 1 meter by 1 meter, filled with mercury.
Go.
That box would have a mass of 13,600 kilograms. Compare that to the same box filled with water that's only 1,000 kilograms.
Wow. Okay. That's a huge difference. Yeah. Really highlights what density means.
Definitely.
All right. Quick conversion check.
Yeah.
Say something has a density of 7.8 GC meter. What's that in kilogmr?
Okay. So you take 7.8, multiply by 1,000. That gives you 7,800 kilogmr.
Perfect. And going the other way, maybe 800 kilogmr?
Right. You divide by 1,000. So 800 divided by 1,000 is 0.8.
Yeah.
0.8 GC meter.
Got it. Being able to flip between those units seems pretty key.
It is, yeah. Especially when comparing different sources or materials.
Okay, building on density now. Let's talk relative density. That's called specific gravity.
Exactly. Relative density is basically just comparing. You compare the density of whatever substance you're interested in to the density of a standard.
And that standard, usually water.
For liquids and solids, yes. Pure water at 4 degrees Celsius specifically. So it's the ratio. Density of substance divided by density of water at 4 degrees C.
A ratio. So does that mean it doesn't have units?
That's the key thing. Because you're dividing density by density, the units just cancel out. Kilograms per cubic meter divided by kilograms per cubic meter, gone.
Ah, so it's just a number. That explains why you often see it written that way.
Yep, dimensionless. And since water's density at 4 degrees C is conveniently 1 gram per cubic centimeter.
Oh. Does that mean the relative density is just the same number as the density in GCMO?
You nailed it. If the density is, say, 3.6 GC meter, the relative density is just 3.6.
And if you know the relative density is, I don't know, 1.4, then the density must be 1.4 GC meter. That's handy.
Super handy. And that number tells you something really useful immediately.
Whether it floats or sinks in water.
Exactly. If the relative density is less than 1, it's less dense than water. So it floats.
Like ice. What's its relative density?
Ice is around 0.92, something like that. So less than 1, it floats.
And if it's greater than 1?
Greater than 1 means it's denser than water, so.
It sinks. Like most rocks or metals.
Simple rule. Less than 1 floats, greater than 1 sinks. Got it. Where does this relative density idea pop up in the real world? Any specific uses?
Oh yeah, quite a few. Geologists use it all the time to help identify minerals. Different minerals have characteristic relative densities.
Okay.
Gemologists, too, distinguishing real gems from fakes, sometimes involves checking relative density.
Interesting.
And for liquids, there are special tools called hydrometers. You float them in the liquid, and how deep they sink tells you the relative density directly. Used for checking battery acid, antifreeze, even milk purity sometimes.
Huh, hydrometers.
Okay.
Let's try putting some numbers to this. The materials have examples. First one's about a piece of iron.
Right. So a piece of iron, volume, 30 cubic centimeters, mass of 234 grams. Find the density and relative density.
Okay, density first. Mass divided by volume. 234 grams divided by 30 cubic centimeters. Carry the one. No, wait, calculator. 7.8. 7.8 grams per cubic centimeter. Perfect. And the relative density.
Well, since the density in GCM is 7.8, the relative density is just 7.8.
Exactly. And 7.8 is much bigger than 1, so.
Sinks. Checks out. Okay, next one. Silver.
Silver. Volume 10 centimeters, mass under 3 grams. We need density in both CGS and SI and relative density.
CGS first. Density equals 103 G, 10 centimeters I.
Yeah.
That's 10.3 GCM.
Correct. Now SI units.
Okay, multiply by 1,000. So 10.3 times 1,000 is 10,300 kilometers.
Spot on. And relative density.
Same as the CGS density number, so 10.3.
Yep. Pretty dense stuff, silver.
Okay, third example. This one's slightly different. We have the relative density and volume, need the mass.
Right. Relative density is 2.7. Volume is 100 centimeters. Find the mass.
Okay, if the relative density is 2.7, then the density is 2.7 GC inertia.
Good start.
And density is mass over volume. So mass is density times volume.
Exactly. Rearrange the formula.
So 2.7 G centimeters times 100 centimeters, that's 270 grams.
Perfect. You see how knowing the relative density directly gives you the density in CGS, which makes the calculation easy.
Yeah, that's a neat connection. Okay, one more. A stone.
This one starts with SI units. Mass, 6,000 kilograms. Volume, 3 cubic meters. Calculate density in SI, density in CGS, and relative density.
Okay, SI density first. Mass over volume. 6,000 kilograms divided by 3 middle days.
Right.
That's 2,000 kilorimolar.
Right. Now CGS density.
Need to convert. Divide the SI value by 1,000. 2,000 divided by 1,000 is 2. So 2 GC middle. Excellent.
And the relative density.
Must be 2, since the CGS density is 2.
Exactly. So the stone is twice as dense as water.
Makes sense it would sink. Okay, these examples definitely help connect density, relative density, and the units.
Good. They really lay the groundwork for the next big idea, buoyancy.
Ah, yes, buoyancy, or upthrust, that feeling of being lighter in water. What's going on there?
It's actually the fluid itself pushing back on you. When any object is in a fluid, liquid, or gas, the fluid exerts an upward force on it. That's the buoyant force, or upthrust.
So it's literally pushing up.
It is. That's why lifting someone in a swimming pool feels easier than lifting them out of it. The water is helping you, pushing upwards.
So when something's underwater, there are two main forces. It's weight pulling down.
Yep, gravity.
And this buoyant force pushing up.
Exactly. And how those two forces compare determines everything: sinking, floating, hovering.
And the weight you feel underwater, your apparent weight, that's just your real weight minus this upward push.
Precisely. Apparent weight equals true weight buoyant force. It's what a scale would show if you stood on it underwater.
And it's not just liquids, right? Gases too.
Yeah.
Like the helium balloon example.
Absolutely. Air is a fluid. It exerts a buoyant force. For a helium balloon, the upward buoyant force from the air it displaces is greater than the balloon's own weight plus the weight of the helium inside. So net force is up.
Which brings us back to the giant iron ship. How does buoyancy explain that? Iron's super dense.
It seems wrong, doesn't it? But it comes down to displacement. The key isn't just what the ship is made of, but its shape.
It's hollow inside.
Massively hollow. That shape displaces a huge volume of water. Way more water than a solid block of iron with the same mass would displace.
Okay.
And the buoyant force is equal to the weight of that displaced water. Displace enough water, and the upward force becomes big enough to support the entire weight of the ship.
So it's about pushing enough water out of the way.
Yeah.
Okay. What main things determine how strong this buoyant force is?
Two primary factors. First, as we just discussed with the ship, is the volume of the object that's actually immersed in the fluid.
The submerged part.
Right. Or, more precisely, the volume of the fluid that gets displaced by that submerged part. More volume displaced means more buoyant force.
The source materials mention comparing a hollow metal cube and a solid one of the same mass. How does that show this?
Okay, imagine both in water. The hollow one is obviously much bigger overall, even if the mass is the same.
Right, because of the air inside.
So when you put it in water, it displaces a much larger volume of water than the small solid cube does. More displaced water means
More buoyant force on the hollow one.
Exactly. That's kind of why a tiny iron nail sinks. But you could take that same iron, flatten it into a sheet, maybe shape it like a little boat.
And it could float. Because the chase displaces more water.
You got it. Volume displaced is crucial. What's the second factor?
The second factor is the density of the fluid itself.
Ah, okay. Denser fluid, more push. Exactly. For the same object, the same submerged volume, a denser fluid will exert a greater buoyant force.
And the example for this is putting a metal cube in fresh water versus salt water.
That's the classic demonstration. Salt water is denser than fresh water. So if you weigh the cube underwater in both, it will seem lighter. Its apparent weight will be less than the salt water.
Why?
Because the denser salt water provides a greater upward buoyant force for the same displaced volume.
Okay, so bigger submerged volume means more buoyancy, and denser fluid means more buoyancy. Got it. This feels like it's leading straight to Archimedes.
It is indeed the famous Eureka moment, Archimedes' Principle.
That's the official statement.
Archimedes' Principle states that the apparent loss in weight of a body when it's partially or fully immersed in a fluid is equal to the weight of the fluid displaced by the immersed part of the body.
Okay, apparent loss in weight. That's the difference between its weight in air and its weight when submerged, right? What we called apparent weight earlier.
Exactly. If weight in air is W rho and weight submerged is W rho, the apparent loss is W minus W rho. Archimedes figured out that this difference, this lost weight, is precisely equal to the weight of the fluid the object pushed aside.
Amazing. And there's an experiment described to check this, using a Eureka can.
Yeah, the Eureka can experiment. It's a classic. You need the can. It's just a container with a spout near the top. You also need a beaker, a spring balance, your object, like a metal cube, and a regular scale.
Okay, step 1.
Fill the Eureka can right up to the spout so it's about to overflow. Put the empty beaker under the spout.
Got it. Ready to catch overflow.
Then, hang your object from the spring balance. Record its weight in air. That's W.
True weight. Next.
Carefully lower the object into the Eureka can until it's fully submerged. Don't let it touch the bottom. As it goes in, water overflows through the spout into the beaker.
And while it's submerged, you read the spring balance again.
Yes. That reading is W euro, the apparent weight in the fluid. It will be less than W.
Because of the buoyant force.
Exactly. Now calculate the difference. 1 minus W euro, that's your apparent loss in weight.
Okay, final step.
Take the beaker that caught the overflowed water, weigh that water using the regular scale. That gives you the weight of the displaced fluid.
And Archimedes says, the apparent loss in weight, W rho, should be the same as the weight of that collected water.
That's the principle. And if you do the experiment carefully, you'll find they match very closely. It's a direct confirmation.
Brilliant. Such a neat experiment. Okay, so armed with density and Archimedes, let's talk about the outcomes. Sinking versus floating. How does it all play out?
It all comes down to that tug of war between the object's weight, pulling down, and the buoyant force pushing up. 3 main scenarios.
Scenario 1.
Sinking. Sinking happens when the object's weight, W euro, is greater than the maximum buoyant force the fluid can provide when the object is fully submerged. The downward force wins.
And density-wise?
This usually means the average density of the object is greater than the density of the fluid, like a rock in water.
Okay. Scenario 2. Hovering. Floating, but fully submerged.
Right, neutral buoyancy. This happens when the object's weight, W, is exactly equal to the buoyant force, W euros, when it's fully submerged. The forces balance perfectly.
In densities.
The average density of the object is equal to the density of the fluid. Think of a perfectly balanced submarine or maybe a fish just hanging out.
Makes sense. And scenario 3. Floating on the surface, partially submerged. Like wood, or us, floating.
This happens when the object's weight, WO, is less than the buoyant force it would experience if it were fully submerged.
So it doesn't need to go all the way under.
Exactly. It sinks just enough to displace a volume of fluid whose weight equals the object's total weight. At that point, buoyant force equals weight, equilibrium is reached, and it floats partially submerged.
And density-wise, this means?
The average density of the object is less than the density of the fluid, like cork, wood, ice, or even ships when you consider their overall average density, including the air inside.
So it really boils down to comparing the object's average density to the fluid's density, which leads nicely into the principle of flotation. What's the core statement there?
The principle of flotation is essentially a refinement for the floating case. It states, a body floats in a liquid if the weight of the body is equal to the weight of the liquid it displaces.
That sounds almost identical to the condition for floating partially submerged we just talked about.
It is, really. It's just stating the equilibrium condition for any floating object, whether it's fully submerged and neutrally buoyant or partially submerged. When something floats, it has displaced just enough fluid to perfectly balance its own weight. That's the key.
Okay. Let's look at some more applications that bring this principle home. The iron nail versus the iron ship is a great one. Any others?
Oh, definitely. Submarines are a perfect example. They use ballast tanks.
Right, you mentioned those.
To dive, they let water into the tanks. This increases the submarine's total weight, making it heavier than the buoyant force, so it sinks.
And to surface.
They use compressed air to blow the water out of the tanks. This reduces the weight, making it less than the buoyant force, so it rises. They actively control their weight to manipulate flotation.
Clever.
Yeah.
What about icebergs? We know they float because ice is less dense than water, but why is so much underwater?
It comes back to the principle of flotation and the densities. Ice density is about 0.92 gcm, while seawater density is roughly 1.025 gcm. They're quite close.
Okay.
So for the weight of the displaced seawater to equal the total weight of the iceberg has to displace a lot of water relative to its total volume. Turns out it needs to submerge about 90% of its volume to achieve that balance.
90%, wow. No wonder they're dangerous. Just the tip showing.
Exactly. That hidden bulk is the real hazard.
And humans.
Yeah.
Our density is close to water, you said.
Yeah, the average human density is very close to fresh water, usually a little less, especially if you take a deep breath. That's why we can float.
Yeah, that takes effort sometimes.
It can. Body composition, lung capacity matter, but remember salt water. It's denser.
Ah, right. So the buoyant force is stronger in salt water.
Which means it's easier to float. Less effort needed to displace enough water to match your weight. That's why floating in the sea often feels easier than in a pool.
That makes total sense now. Okay, fish and balloons too.
Yep. Fish often have a swim bladder. It's an internal sac they can fill with gas or deflate.
To control buoyancy.
Exactly. Inflate it, volume increases, more water displaced, buoyant force increases, they rise. Deflate it, they sink or maintain depth. Balloons, like hydrogen or helium ones, work because the gas inside is way less dense than air.
So the weight of the air they displace is much more than their own weight.
Way more. So the net force is strongly upwards. They rise until the outside air becomes thin enough, less dense, that the weight of the displaced air finally equals the balloon's weight. Then it stops rising.
Flotation in air. Cool. And lastly, those instruments. Lactometers and hydrometers.
Both work directly on the principle of flotation. They are designed to float, and how high they float depends on the density of the liquid they're in.
So a denser liquid pushes them up more.
Right. In a denser liquid, the instrument needs to displace less volume to match its own weight, so it floats higher. In a less dense liquid, it sinks lower. They have calibrated scales on the stem.
So you just read the scale at the liquid surface.
Precisely. A lactometer is calibrated specifically for milk densities to check for purity. Watered-down milk is less dense. A hydrometer is more general purpose for various liquids.
Fascinating. It's all about that balance point where weight equals the weight of the displaced fluid.
Yeah.
Great examples. Okay, let's quickly nail down the key takeaways from all this.
Sounds good. So density, mass per unit volume. Key units kg and GCM. Remember, 1 GCM now equals 1,000 kg an hour.
Relative density.
Right.
Compares substance density to water density. No units, just a number.
Buoyant force. Upward push from the fluid. Depends on displaced volume and fluid density.
Archimedes Principle. That buoyant force equals the weight of the fluid displaced. This causes the apparent loss of weight.
Principle of flotation. Things float when their weight equals the weight of the fluid they displace.
That density comparison tells you what happens. Object denser than fluid sinks. Densities equal floats, fully submerged. Object less dense floats partially submerged.
Don't forget, a floating body's apparent weight is 0. And buoyancy works in gases too, not just liquids.
Excellent summary. These ideas really do connect everything together.
They build on each other very logically.
Okay, so we've covered a lot. Thinking back to the start, that giant ship floating, the balloon rising, hopefully that feels less like magic now.
Hopefully more like understandable physics. It's about displacing fluids and balancing forces.
Definitely. What seemed counterintuitive is just these principles playing out. So here's a final thought to chew on. We've seen how density differences in buoyancy govern floating in water and air. Where else might these principles be subtly at work? Maybe in systems we don't usually think of as involving fluids or floating. Something unexpected.
That's a great question. It makes you think about things like convection currents in the atmosphere, oceans, or even geological processes deep within the earth.
Yeah.
Maybe even sorting processes in industry.
Yeah. Lots to explore. We definitely encourage you to keep thinking about how these fundamental ideas apply all around us.
Absolutely. Keep your eyes open for density and buoyancy in action.